Start this new way of taking the derivative, which is using this method called the chain rule. And you will use the chain rule repeatedly. This is not going to go away, so you need to get very comfortable with it. And this is one that tends to take a lot of practice, I guess, to get comfortable with it, because I see students kind of stumble with it, but it seems like those who stumble with it are those who are not getting their homework done. So evidently, it's just living proof that you need a lot of practice on this one. Okay, so this is section 3.6, chain rule. Chain rule. Sounds like something a prison inmate would name. I don't know why my mind is going there. That's just crazy. Chain. Okay, so just a little bit of a preview. You might not like this preview, but it's good for you. All right, suppose somebody gives me this polynomial, and it is 3x squared plus 1 to the 5th power, and they want me to take the derivative of that. We've never done that before. So there needs to be a way to make this happen. And the chain rule kind of comes into play where you have a polynomial, often a binomial, to some exponent. So the way we do this is where they come in with this chain rule thing. Well, your goal is to find y prime, which is dy dx. And when we say dy dx, that means this is written as y equaling stuff with the x variable. So, but to find this, we're going to go through this almost composition of functions where we're going to say dy du times du dx. Now, if you really form the product, the du's cancel, and you do have dy dx sitting there. So this is all fair game. So now I need a u function. So if I have dy du, that means I need to have a function that says y equals u information. So what I'm going to do is claim this as y equaling u to the 5th so that I can take a dy du. Then to do du dx, this is a u equaling x information. And so this one is going to be the 3x squared plus 1. So now I have to have a dy du and a du dx. Well, my dy du is just going to be 5u to the 4th. My du dx is just going to be 6x. So with all this written now, my y prime is dy dx, which we can write as dy du times du dx. So let's plug in what we know. We know that dy du, we just stated, was 5u to the 4th. And we know that du dx, we just came up to be 6x.
Times 6x?
Times, that's a times multiplication. I could put it on parentheses, but it's a little cleaner in this case to put it as a multiplication. It might help if you kind of wrap this down here to let you know that this was kind of like the work that took us to that end result. Maybe that'll help you. Now, we have one more issue, and that is this is dy dx, which means y equaling x information. Well, what that u is like, what is it doing there? U can't be there. So I've got to replace that u back with what it equals in x terms, which is up here, 3x squared plus 1. So I've got to get rid of the u, because this is dy dx. It says nothing about u. So u's got to go. So replace that u with the 3x squared plus 1. That's right. That's about the truth. That's kind of the attitude. U has got to go. And then if you wanted to clean this up, this would be 30x times 3x squared plus 1 to the 4th power. And that would be your answer. So if y equaled 3x squared plus 1 to the 5th, y prime equals 30x times 3x squared plus 1 to the 4th power.
Okay, so why did you just, from the top, y prime equals y here?
Because I didn't know how to take the derivative of this. So the only way I can do it is to break it into parts, which means to break this whole function into two functions and kind of play around with them, pull it back into that statement, and come to the result where actually I took the derivative.
Okay, and how come the y equals u to the 5th?
Why does y equal to u to the 5th? Because I made that up. Okay. All this by, yeah.
Then you can replace everything in parentheses with the u.
It's a composition of two functions, really. It's a composition of two functions.
Why couldn't you designate, like, why did you designate y equals if not y equals 3x squared plus 1?
Let me show you something. You're not going to like this, but I'm going to show it to you. Okay. Go to the board.
You can't change what y equals, but you can make up a letter and say that it equals.
That's true. You can't change what y equals, but you can make up a letter. That makes sense. That helps. I'm not being sarcastic. It really does. Okay. Okay. After I said it, I thought that sounded a little bit.
Any letter that's not defined yet.
And change it around. Okay, here's the chain rule, and here's what I just showed you. Okay, this dy dx business is being dy du dx thing. Well, here it is as a composition of functions, and here's kind of a vision of it. You know, they're kind of trying to show it to you up here in a kind of a graphical sort of like image. Okay, but this is what's going on. I'm not going to push this because the chain rule is going to give me a shortcut. There's a definite shortcut to this. But I kind of wanted you to see the underlying reasoning for how the shortcut works. Okay, so it's nice. You don't have to get into this. You don't have to worry about this. But I wanted you to definitely see this. Yes?
Well, I was just going to ask, like, for my math lab or whatever, would that be the final answer they would want? Or
This is what they want.
Okay.
There might be one question playing in this. I can't quite remember what I did, but this is where you're going with
You
it.
don't ever have to expand it.
No, you don't want to expand it. That would not be fun. It could happen, but that would take you a while. Okay, you could. You're right. You could, but that would not be fun. Now the shortcut is, and I'm going to show you the shortcut. The shortcut, I'm going to write it real quickly, and then maybe you can see how it works. Is that if you have d dx, and we've already seen a little bit of this, of u to the nth power, then this, how did I do that? I didn't write that right. Hold on, let me rewrite. I got the notation wrong. If you have d dx of u to the nth power, it equals n times u to the n minus 1. We've already done this, right? We've already done this. Where you pull the power out front and then you decrease the power by 1. But then you have to take the du dx because you threw x and you threw this new u variable into the picture. Because you made up this new u variable, you've got to deal with it. Okay? So, looking at this example, I don't know if I can get it all on the page or not. I might can. No, is it going to fit? Yeah, barely. Okay. So what you do is you pull the 5 out front. So I guess I could write it. Maybe here, let's write it here beside it. So if we have, our case was y equaling 3x squared plus 1 to the 5th power. So according to this new setup, I pulled the exponent, the n to the front, pulled the 5 to the front, write the u, which is the 3x squared plus 1, then the n minus 1, which is take the 5 minus 1, which is 4. So you pull the exponent to the front, and you decrease the exponent by 1. Then the du dx is to take the derivative of this that was u, or this polynomial that was being to the power of 4. So the derivative of 3x squared is 6x plus 0, or 6x, right? So you take the derivative of what's inside. Du dx is the derivative of that u, which is the stuff inside here. And then that turns out to be the answer. Okay. So pull the power to the front, decrease the power by 1, and then take the derivative of that polynomial, which is usually a binomial, in the parentheses. That's your shortcut. Okay. Now, one more, well, now let's just do some examples. It just takes a minute to kind of get the flow of it. I kind of understand why they call it the chain rule, but in ways, too, it's a little bit interesting why they named it that. Okay, so suppose we have a very similar example. Suppose we have y equaling 5x cubed minus x to the 4th, all to the 7th power. and we want to take the derivative, and we're going to use what we call the chain rule. Well, the derivative of this, and remember this is like a binomial or some kind of polynomial to an exponent, you pull the 7 to the front, then you decrease the 7 by 1, and then you take the derivative of everything in those parentheses. That's the chain. Take the derivative of what's in the parentheses. What's the derivative of what's in the parentheses is 3 times 5 is 15x, decrease it by 1 squared. And then 4 times 1 is 4, and 4 minus 1 is 3. And that's the derivative of what was inside. Yes, they're going to want that 7 times this, and that's it. I don't think they're going to ask you to distribute. So if you take the 7 times the 15x squared minus the 4x cubed, oh, what is 7 times 15? Do I have it written? Okay, very good. 105x squared minus 28x cubed times 5x cubed minus x to the fourth 6. When you have an exponent like 6, they're not going to ask you to expand that. You're going to be able to stop at this point. But I really think they're going to have you multiply the 7 times that ending binomial. Let's try another one. Suppose you have y equaling 1 over 3x squared minus 4 to the power of 8. Any suggestions? There you go. Go ahead and rewrite this as 3x squared minus 4 to the negative 8 power so that the chain rule becomes very obviously applied. So then when you take the first derivative, pull the exponent to the front, then decrease the exponent by 1. So negative 8 minus 1 is negative 9. Then take the derivative, this is the chain, take the derivative of this little polynomial in here. 3x squared, the derivative of 3x squared is 6x, and the derivative of minus 4 is just 0. So it's 6x really plus 0, or just 6x. There you go. Negative 48x. Actually, you're going to go ahead and bring it down, right? 3x squared minus 4 to the 9th power. Okay, suppose you have this one. Y equals the square root of 3x squared minus 4x plus 6. There you go. You're going to write this as a 1/2 power. So it's kind of sitting in the position of a chain rule situation. So you're going to rewrite this as 3x squared minus 4x plus 6 to the 1/2 power. Then when you take the derivative, you bring the 1/2 in the front. What's 1/2 decreased by 1? Negative 1/2. And then take the derivative of everything inside those parentheses. The derivative of 3x squared is 6x, and the derivative of a negative 4x is a minus 4, and the derivative of plus 6 would be plus 0, so we're just going to leave that off. So when you take the 1/2 times the 6x minus 4, it becomes 3x minus 2. And then this negative exponent is going to drop it, and we're going to convert it back to the radical, okay? So it's going to bring it down, and I'm going to convert it back into the form of the radical. And there's your first derivative. Okay. Take a look at this one and tell me what you would do. 3x squared times 2x cubed minus 5 to the 4th power. Okay, just thinking about this, what are you going to do to this?
Do the chain rule first.
You gotta take the derivative of the next one first.
Right, first you have to write down 3x squared. And then you have to take the derivative of that other
Okay,
and
product rule.
add the
There you go. It's the
first part.
product rule, right?
That second part.
It's the product rule where the 3x squared is the first and this 2x cubed minus 5 to the 4th power is the second. So then when you apply the product rule and you have to do the derivative of the second is going to require the chain rule. So again, the chain rule is nested inside the product rule. Okay, the chain rule is nested inside the product rule. So this will be the first, which is 3x squared times the derivative of the second. But the derivative of the second is the chain rule. So I'm taking the derivative of the 2x cubed minus 5 to the 4th power. So that's going to be 4 times 2x cubed minus 5 to the 3. And then the derivative of what's inside here, which is going to be 6x squared plus 0. That's all a big product. That's the first times the derivative of the second. That's one term. Everything is multiplied there. That's one term. So you're going to end up saying 3x squared times 4 is 12x squared times 6x squared is 72x to the 4th. Okay, that's the first times the derivative of the second plus the second times the derivative of the first. Okay, the second is 2x cubed minus 5 to the 4th power, and the derivative of the first is 6x. There you go. So now let's clean it up a little bit. With the derivative is done. We have accomplished taking the derivative. Now we just want to simplify this. So 3x squared times 4 is 12x squared times 6x squared is 72x to the 4th, right?
Why are you multiplying 3x squared times 4?
I'm just cleaning it all up.
Wouldn't you multiply the 4 times 2x cubed minus 5?
No, because this is cubed. All this is attached to that exponent of 3, which would be a horrible, it's a big old expansion, right?
Oh, okay.
You see that? Okay, you can't go into this guy. Okay, and over here, you just have 6x times 2x cubed minus 5 to the 4th power. Oh, y'all aren't going to like what I'm getting ready to do. There's a greatest common factor sitting here
It's 2x cubed minus 5
to the power of,
to the power of 3.
there you go. So this is 2x cubed minus 5 to the power of 3 times, right?
So 2x
Plus what? 6x times 2x cubed minus 5 to the first, right? Okay. So this is 2x cubed minus 5 cubed times 72x to the 4th plus 6x times 2x cubed. This is just the first power, so I can distribute. 6 times 2 is 12, and x times x cubed is x to the 4th. Oh, could I have? Yes, I could have, and I didn't. Shame on me. Could have taken more out. What do I have in here? 72 and 12 is what, 84, x to the 4th? And I really could take out more out of here, right? What's the GCF of that thing? Is it 6x? Something more than 6? Okay, 6x, so we'll take it out. So this is 6x. Leaving behind, what is it? 6 goes in there how many times? 14? There you go. Now, the next one's weird, and I want you to write on here, whoa, watch out, okay? Okay, this one's kind of interesting. And this is one you have to be really careful with, that you don't confuse it with the second half of the lecture in this section. Okay, suppose they say that y equals sine to the fourth of x. Sine to the fourth of x is the same thing as sine x to the fourth power. Okay, so this could be rewritten as sine x to the fourth power, right? Sine x times sine x times sine x times sine x. So we can apply the chain rule. So the first derivative becomes 4 times sine x to the power of 3. And then you chain rule, take the derivative of sine x, which is cosine x. So this is 4 sine cubed x cosine x. Now, dare the argument of the trig function. When I'm talking about the argument of a trig function, this x, had that said sine to the fourth, or sine to the fourth of 5x, or sine to the fourth of 3x plus 5, something like that, you probably wouldn't want to do this, okay? There's another way. All right, so you got to be kind of careful. But it does work when the argument of the trig function is just x, and I guess it would work the other way, but that's not quite normally how we would do it. Okay, so far we have applied the chain rule to really what we call polynomials to a exponent, a binomial to an exponent, a trinomial to an exponent, so forth and so on. But we can apply the chain rule also to trig functions, which is what we're getting ready to do. So chain rule on a trig function. Okay, chain rule with the trig function. Okay, and this is how that kind of plays around. If you have something like y equals sine of 3x, where the argument of the trig function is the 3x, it's not x anymore, it's 3x. When you take the derivative of a trig function, you say the derivative of sine 3x, the derivative of sine x is cosine x, so the derivative of sine 3x is cosine 3x. But the chain rule says now you got to come back and take the derivative of the argument. You got to take the derivative of the 3x. And what is the derivative of 3x? 3. Okay, so you have to take the derivative of the 3x. So when it's not just x, if it's 3x or 2x plus 5 or whatever, you have to come back and take the derivative of it. So really the first derivative is 3 cosine 3x. It's not cosine 9x. Be really careful. That 3 is times all of cosine 3x, which means we put it in the front. And that's where you have to be very careful when you're writing your answer, that you're not multiplying times the argument. So what if they say y equals 4 over 3 pi sine 3x plus 4 over 5 pi cosine 5x. They want you to take the derivative of that. Well, it's not bad. Now that we have this chain rule, it's really quite simple. Remember, when you take the derivative of a constant, the constant kind of comes out front. So you keep the 4 over the 3 pi. The derivative of sine 3x is cosine 3x times what? What's the derivative of 3x? 3. And this next one, you keep the constant 4 over 5 pi, just write it down. The derivative of cosine of 5x is a negative sine of 5x, but then you got to take the derivative of the 5x, which is 5. So this answer is, this 3 times the 4 over 3 pi, the 3's reduce out, giving a 4 over pi, cosine 3x. And on the second one, the 5's are going to cancel. I should have written this as subtraction. 4 over pi sine 5x. Not bad. Suppose we have y equaling x tangent 2 square root of x plus 7. Well, I don't like that. When you see a radical, you're going to need to convert it to an exponent of 1/2. Here we go. Now, how are you going to take the derivative of x tan 2x to the 1/2 power? Come back. What rule is that? That's the product rule. First times derivative of the second plus the second times derivative of the first. Okay, that's the product rule. Okay, so the first times the derivative of the second. The first is x, and the derivative of tan 2x to the 1/2. The derivative of tangent is secant squared x, right? So the derivative of the tan 2x to the 1/2 is secant squared 2x to the 1/2. But then I got to take the derivative of the argument of that secant function. What's the derivative of 2x to the 1/2? 1/2 times 2 is 1, x to the negative 1/2. That's the first times the derivative of the second. Now you have the second times the derivative of the first. Well, the second is tangent of 2x to the 1/2 power. I should have put the, times the derivative of x, and the derivative of x is 1. And then, we forgot this plus 7 out here. What's the derivative of 7? 0. And I'm going to go ahead and put that on there so you can see the product rule and then what's left outside the product rule. I mean, I didn't have to put that except for to kind of help you kind of be able to organize what's going on. Okay, so the derivative has been taken. What in the world do we have? Let's clean it up a little bit. Okay, x times x to the negative 1/2. What is x times x to the negative 1/2? It's x to the 1/2, which is the square root of x. I'm going to go ahead and write x to the 1/2. And then this is secant squared 2, and I'm going to go ahead and write this. I'm through taking the derivatives. I'm going to replace that with the square root of x. That one's easy to replace. Okay, and then here I have tangent of 2 square root of x. Not bad. So the answer is square root of x, secant squared 2 square root of x. This is a really ugly answer. Okay, that's a really ugly answer, but whatever. Okay, let's try another one. This is interesting. Got to really be thinking on this one. Y equals sine of cosine of x. Wow, how do they come up with these questions, right? Come up with this mess. But she's at the bottom of the page, so it must not be too bad. Okay, so what we're going to do, just act like this is x. The derivative of sine x is cosine x. But then you're going to come back and take the derivative of the argument of the function, which is cosine x. You see that? The derivative of sine x is just cosine x, where I'm like replacing all this with x. Or if you want to call it sine theta, the derivative of sine theta is cosine theta, but theta is all that mess underneath my finger. Okay? So the derivative of sine theta is cosine theta, but theta is all that mess that was under my finger, which is cosine x still. Okay, so the derivative of sine theta is cosine theta, but theta is all that stuff under my finger, which was cosine x. Okay, but then I have to take the derivative of cosine x by the chain rule. Right? Because it's sine theta d theta. It means sine theta and the derivative of what was there. So the derivative of cosine x is a negative sine x. And that's the answer. This is not cosine squared x, right?
So
Okay, this is cosine of cosine x. There you go. This is the argument of the cosine function. So that's kind of a tricky, an appearance thing. Okay, the appearance of it's really weird. You know, here's what I think. When I see something like this, when I take the derivative, I'm thinking sine theta d theta. Okay? So if this is theta, sine theta, d theta. You see that? Okay? Kind of the same, well, sort of. When I took the derivative of tangent of 2x to the 1/2, this was tan theta. The derivative of tan theta is secant squared theta d theta. So this is secant squared theta d theta. Okay? And that's really kind of what I have to think and almost say in my head in these as I'm going through them.
Why didn't you just stop right there?
On this one? Because remember I had the product rule. The first times the derivative of the second. First times the derivative of the second plus the second times the derivative of the first. This was a product. First times the derivative of the second plus second times the derivative of the first.
Okay, and that's what you got this one from. And then how come you just kept going? So just make it.
Hold on. This is the first, right? All of this was the derivative of the second.
Okay, gotcha.
You see it? First, derivative of second. Second, derivative of first. Got it now? Okay. Maybe, sort of. It'll come. Eventually it'll somehow decide to sink. Right? So what if you have y equaling sine of cosine of 2x? Okay. Okay. So this is like theta. Okay. This is like theta. So y prime is sine theta d theta. Right? So I can even add another step on here. Y prime is sine theta. No, it's not. Y prime, okay, the derivative of sine theta is what? Cosine theta. So y prime is cosine theta, but the theta is all that mess underneath my finger. Y prime is cosine theta, but theta is everything underneath my finger. Then I got to take the derivative of that cosine 2x, right? So if I'm taking d dx of cosine 2x, what does that equal? Derivative of cosine is negative sine, and then the chain rule says I got to come back and take the derivative of the 2x, which is 2. Okay, so the derivative of cosine 2x is negative sine 2x times 2. And you really do think very independently off to the side that derivative. So you don't look at the rest of the mess written on the piece of paper, just thinking, what is the derivative of cosine 2x? And then when you write it down, you got to step back and say, what in the world is all that? Where is what going on? And so this result is negative 2 sine 2x and cosine theta, which is really cosine of cosine 2x. Like this is theta. Okay, treat the cosine 2x as if it's theta. These are pretty difficult, okay? These are pretty deep. And when you're doing your homework, when you've done like 10 questions and then you hit this one, it will come a little faster to you. Okay, so when you do several questions and you get the chain rule a little better in your head, then this will come to you a little easier. Okay, suppose we have this one. Y equaling 1 plus cosine 2x to the power of negative 4. Now what? This is like both chain rules. The chain rule before the trig function and the chain rule after the trig function. Okay, so the first derivative, pull the negative 4 out front and decrease the negative 4 by 1. Then take the derivative of what's in here, which is 0 plus the derivative of cosine 2x. What is the derivative of cosine 2x? Negative sine 2x times 2. So the derivative of cosine 2x is a negative 2x times 2. Negative sine 2x times 2. Okay, here's your thinking kind of independently for a few seconds to get that result. So this is negative 4 times a negative 2 is a positive 8 sine 2x, and really you should put that all in the denominator now, 1 plus cosine 2x to the 5th power. Okay, one more. Suppose you have y equaling, this is weird, sine cubed of pi x minus 2. Remember we put a little asterisk by 1 before we went into this section? Not this section, this part D or whatever it is. And I said this one's kind of weird. And we said sine cubed x was sine x cubed, or it was sine to the 4th of x or something, remember? Okay. Wherever it is, it's somewhere back there. And I remembered to put a big old asterisk on it. Here it is, right here. Way back in the same notes of this section, we did this one. And so this is going to be similar to it, in that we're going to rewrite this one as sine of pi x minus 2 all cubed before we take the derivative. I've not taken a derivative, I'm just rewriting the question in another form. Okay, chain rule, here it comes. First derivative. Pull the 3 out front and decrease the 3 by 1. Then take the derivative of what's inside those square brackets. The derivative of what's inside those square brackets, as if this is theta, is going to be the derivative of sine theta is going to be cosine theta d theta. So you're going to write cosine theta, pi x minus 2, d theta. Okay, so the derivative of what's in these square brackets is cosine theta, where theta is this pi x minus 2 mess, and then d theta, which is the derivative of what's in these parentheses, which is pi. So it's almost nested chain rules, okay? Okay, but if you think of this as sine theta d theta, okay, sine theta, the derivative of sine theta is cosine theta, and d theta is the derivative of the pi x minus 2. That's what you're thinking. If this had just said sine theta, then the derivative of it would be cosine theta d theta. Cosine theta d theta. And that's what that is. I think that makes it a little bit easier. So now what is all this? We equal, is this a mess? Let me see. 3 times pi times cosine. Okay, so this is 3 pi cosine pi x minus 2. And then I'm going to rewrite this back as sine squared pi x minus 2. And there it is. Okay, you're all looking a little bit concerned. You're all very serious in this room right now. Okay, I may be like at the overload point. which is good because that's the end of the section. So the chain rule applies to two major things, a polynomial to an exponent and a trig function where the theta of the trig function, the argument of the trig function, is more than just x. Okay, guys, go and do. Have fun doing your homework, and I'm not being sarcastic.